Next, we will introduce the fundamental theorem of calculus. Let's recall the definitions of the definite and indefinite integrals. At first glance, they appear to have nothing in common. One is the area and the other one is the general antiderivative. The fundamental theorem of calculus has two parts that serve two purposes. One, it confirms that the integration and differentiation processes are the opposites of one another. And secondly, it establishes a clear connection between the two types of integration. We already know that the indefinite integral of a derivative of a function will give the general antiderivative generated by the function. So in some sense, integral undoes the derivative. So can we undo the antiderivative by differentiation? We run into issues right away. Because the general antiderivative is not a single function, but rather a collection of functions, this expression simply makes no sense. Can we try to differentiate the definite integral instead? Well, this is not fun either, because derivative of a constant is always zero. So how exactly are we going to show that derivative undoes the integral? We introduce a cumulative net area function that computes the net area under the function f from a to some value x. As x changes, the value changes, thus this expression is a function of x. Therefore, we can differentiate this with respect to x. So what is the derivative of the cumulative net area function is equal to? Well, according to the fundamental theorem of calculus, it is equal to the function itself, evaluated at x. And this is the first part of the fundamental theorem of calculus. Let's do an example and find the derivative of the following function g, which is a function of x, despite the fact that the variable of integration is t. According to the fundamental theorem of calculus, the derivative is the function in the integrand evaluated at x. Similarly, let's find the derivative of the following function h, which is a function of x, despite the fact that the variable of integration is xi. According to the fundamental theorem of calculus, the derivative is the function in the integrand evaluated at x. Now we can merge the first statement of the fundamental theorem of calculus and the chain rule to create the following rule. Let's find the derivative of g by applying the fundamental theorem of calculus and the chain rule together. We plug in the square root of x into the integrand and multiply by the derivative of the square root. Similarly, let's find the derivative of h of x by applying the fundamental theorem of calculus and the chain rule together. We plug in the x squared into the integrand and multiply by the derivative of x squared, according to the rule. The second part of the fundamental theorem of calculus states that the definite integral of f of x from a to b is equal to the difference between the antiderivative evaluated at b and a, which we denote with the following notation. For example, to find the definite integral of 2x from 0 to 1, we can use the fundamental theorem of calculus and the table of antiderivatives, and then evaluate the difference between the antiderivative at 1 and 0. Of course, we can check this answer by graphing the function and finding the area under the graph on the interval from 0 to 1, which is equal to 1. In summary, the second part of the fundamental theorem of calculus relates all definite integrals to indefinite ones. This relation allows us to focus on developing integration techniques for finding the indefinite integrals without worrying too much about the definite integrals. We introduced and discussed both parts of the fundamental theorem of calculus along with its applications.